everyone, and welcome to Math 8 BCPS-TV style. I'm Mr. Parker, and I'll be your host as we work through today's lesson, which is all about transforming shapes. So why study transformation? Well, when you tile a floor, or create some kaleidoscope art, or edit your photos, you might just be using the ideas of transformation. Today's lesson will cover these objectives, which are the same as week 4 of the Math 8 BCPS remote learning packet, which is the week of April 27th. Students will understand that a transformation is a rule that maps a set of points to a new set of points, experiment with reflections, rotations, and translations. Our first objective is to understand that a transformation is a rule that maps a set of points to a new set of points. Time to think about some transformations. Pick the picture that you think doesn't belong. You may have done this routine in your class before. If you haven't, know that there is no wrong answer as long as you can justify your choice. If there's someone watching with you, invite them to pick one too and share your answers together. I chose B, and the reason that I chose B is because it is the only picture that has a shape in the 4th quadrant. Let's see what my family had to say. Here was what Kayla thought.
I chose C because C is the only one with quadrilaterals.
Jacqueline chose D because she said it's the only one where there's not a reflection over an axis, and this is the only one that actually intersects with an axis. So let's learn a little bit about it. A transformation is a rule or function that maps a set of ordered pairs as inputs to a new set of ordered pairs. The Think About It has 4 examples of transformations, where one shape is the original or input set of ordered pairs, sometimes called the pre-image, and the other shape is the new output set of ordered pairs, sometimes called the image. Each point in the pre-image corresponds or is mapped to a point in the image. Let's look at some specific examples. Let's look at some examples for transformations. Here we have a triangle that has the points 1, 1, 3, 1, and 4, 2 as its vertices. This time, let's try a transformation that maps or changes each ordered pair of the triangle to be a new ordered pair and will create a new triangle. In this case, let's try the rule. We're going to multiply the coordinates by 2.5. So the first coordinate, 1, 1, will become 2.5, 2.5. And you can see that point has been plotted on the graph right there. Let's transform the other points. 3, 1, 3 times 2.5 is 7.5. 1 times 2.5 is 2.5. There we have our second point, and the program has connected those points for us. And then last but not least, we've got the point 4, 2. 4 times 2.5 is 10. 2 times 2.5 is 5, and we have a second triangle. How are these two triangles related? What's the same? What's different? Let's look at another transformation. Here we have a trapezoid. For this transformation, what we're going to do is we are going to swap the x and y coordinates. So here we have the point 1, 2. For my new polygon, my new trapezoid, we're going to swap the x and y coordinates and label the point 2, 1. What do you think is going to happen to this shape when we continue to reverse all these coordinates? Let's see. The point 2, 4 will become the point 4, 2. The point 1, 6 will become the point 6, 1. And lastly, the point negative 2, 2 will become the point 2, negative 2. How are these shapes related? How are they the same? How are they different? And let's look at one more example. Let's try one last example. In this case, what we're going to try is we're going to try to add 4 to each x coordinate and 4 to each y coordinate. Now, before we actually perform this transformation, what do you think is going to happen? How do you think the shape will change? Let's give it a go. So my first coordinate is the point 2, 2. If I add 4 to the first coordinate, the x coordinate, I get 6. And if I add 4 to the y coordinate, I also get 6. Now let's try
-1, 1. If I add 4 to -1, I get +3. If I add 4 to +1, I get 5. And then last but not least, if I add -2 and 4, I get +2. And -3 and 4, I get +1. And here is my new shape, the transformation of the red shape by adding 4 to the x and y coordinates. So again, how are these shapes the same? How are these shapes different? What has changed about this shape? What has transformed?
Our second objective is to experiment with reflections, rotations, and translations. In order to do this, we're going to have to understand the vocabulary a little bit better. Let's think about it. What comes to mind when you hear the word reflection? Did you think of a mirror or a body of water like this? What about the word rotation? I know when I hear the word rotation, I think about the Earth rotating on its axis. How about our last word, translation? Did you associate that with language and changing between languages like I did?
Let's do a little experimenting with reflections. Here we have a pre-image, which is the shape on the left side of the line in red, and we have a line of reflection, which is represented in purple, and then the image of the reflection of the red shape over the purple line. Now, just like a mirror, you'll notice that the shape on the other side of the line of reflection looks the same size, same shape, except it's been flipped and it is backwards from the shape that is on the left side of the line. So let's move some points around and see what we notice. When I move the points on the red shape, because this purple line is acting like a mirror, the points on the black shape are moving as well, and they're staying just as far away from the purple line as the red shape. The closer I get to the purple line with the red, the closer the black shape gets to the purple line. I can also move this purple line to get some different reflections. If I move the line, then the shapes move, the black shape moves as well. Just like if I were to move a mirror, my reflection image would move as well. Let's do some fun stuff. What happens if I cross the line? Don't cross the streams, just like Ghostbusters. Oh, okay. So I can, unlike a real mirror, which I wouldn't suggest trying to go through, in geometry, we can go over a line of reflection, which means that our pre-image will be on both sides, and therefore our image will be on both sides of that line of reflection. Now let's take a look at rotations. Here, the original shape, or the pre-image, is the triangle made with the green, blue, and red points. The image, or the action after the rotation has happened, is represented by the red triangle. The purple point represents the center of rotation, or the point that I am rotating around. So let's move some points and see what happens to the red triangle. Well, as I move the points on my pre-image, the points on my image are moving too, because they should be the same size and shape. If I move my center of rotation, I can see that my image is also moving. Over here on the left, I have the number of degrees of rotation. That's how far it's actually been rotated. So if I put this to 0, here I haven't rotated any degrees, and you can see one shape fits right on top of the other. The further I rotate it, the further away it goes until, well, it starts coming back. And now, oh, well, that's weird. It mapped right back to itself, but it's not at 0 anymore. It's 360, because if I go all the way around a circle, rotate 360 degrees, I'm right back to where I started. So this is interesting between 0 and 360, but 0 and 360 are a little tricky to see. I can also move the center of the rotation to actually be a point on the shape, and I can rotate my shape like that. What do you notice? What is staying the same? What is changing as we rotate our shape around a given point? For our last transformation, let's look at translations. A translation is a slide across the coordinate plane. So in this case, our pre-image is the black quadrilateral and our image is the purple quadrilateral. Now, we also have this little triangle over here, which tells us how far to slide our shape. So I'm going to move this point to somewhere that's going to be a little easier for us to work with the coordinates here. So this point is now at -4, 2. What this triangle is telling us is that we are going to slide all of our points to the right 6 and up 2. So if I started at -4 and I slide over 6 and then up 2, you can see that this point is mapped to this point. They are corresponding points because they represent the same point just under a transformation. Similarly, and it's a little tougher here because we don't have those nice round coordinates to work with, but if I move 6 units this way and then 2 units up, I am at that point. So let's move some things around. If I change my original pre-image shape, it changes my image. That's pretty much what we have seen with the other rigid transformations. Now let's see if we move this point. What do you think is going to happen? Well, if I move it to the left, then it means it's translating not as far to the right. If I move it below the x-axis, now it represents a translation that is to the right and down. And if I slide this point over here, now my pre-image is moving to the left 6 units and down 2 units. What's the same? What's different when we do a translation?
If you'd like to experiment with transformations at home, all you need is a piece of paper, a second piece of paper or tracing paper, if you have hamburger patty paper, or if you happen to be like me and have a school supply store in your closet because you're a teacher, you might have some clear transparencies or pocket protectors that can help you out. That's what I'll be using today. And what we're going to do is just trace our shape. So I'm going to use my whiteboard marker here. I'm going to try really hard to make it nice and exactly the same copy. A little flare there at the end, that's okay. But we can see that those shapes are the same. To perform a translation, all you have to do is slide the top paper wherever you like. That will be a translation. If you would like to rotate it, simply turn the top paper. And now I can see my arrow is pointing down because I turned it 90 degrees. The last transformation that I can do is I can flip this protector over and now my arrow is facing a different way. So there we have it. Those are the 3 rigid transformations: reflection, rotation, translation. In each case, the size and shape of my image was the same as the size and shape of my pre-image.
Reflections, rotations, and translations are referred to as rigid transformations. Rigid means not changing. What are the characteristics that are not changing during these types of transformations? Well, there are 3. The first is the side lengths. If we look at any 2 of these rigid transformations, the pre-image and the image, I can see that this length here and this corresponding length here are exactly the same. So the side lengths stay the same. The second characteristic that stays the same is angle measures. All of these Fs have 90-degree angles in them, and all of the pre-images and images have 90-degree angles in them. All of the angles have remained the same measure. Lastly, parallel lines are taken to parallel lines. If I look at a pair of parallel lines in one of my original shapes, the pre-image, this line is parallel to this line. In the reflection, I can see that this line is still parallel to this line. If we look at the rotation, if I look at the back of the F and the front of the F, those lines look to be parallel. And over here, even though they're rotated, that line segment and that line segment are still parallel. And lastly, with translations, if I look at the top of the F and the middle of the F, the top of the F and the middle of the F, they are all parallel. This is an example of a dilation. This type of transformation is different from rotations, reflections, and translations because the size of the pre-image and image are different. So now try one on your own. Here are some questions to answer about this transformation. The first one has been done for you. Number 1 asks, what is the image of A, which has coordinates of -6, 2? The answer is A prime, which has coordinates of 6, 2. Question 2 asks, what is the pre-image of B prime, which is 5, 6? Did you get B, which has coordinates of -5, 6? If you did, you're doing well. Awesome. Question 3 asks, what is the image of C, which has ordered pair -3, 7? Did you get C prime, which has coordinates 3, 7? Fantastic. Number 4 asks us which side is congruent to CD. Now, congruent is a vocab word that we'll dive a little deeper with next week, but for now, we'll say the same size and shape. So which segment has the same size and shape in the image as side CD? Did you say side C prime, D prime? Awesome, you're on a roll. All right, similarly, question 5 asks which angle is congruent to angle D? What do you think based on what we just said about what it means to be congruent? That's right, D prime. Awesome. Last question, number 6, asks how you would describe the reflection. So there's no single correct answer here. Personally, I would say that this is a reflection over the y-axis because the y-axis is acting like the mirror. If I was standing at quadrilateral ABCD and my mirror was right here, ooh, that was a really good straight line, then A prime, B prime, C prime, D prime would be the reflection. That would be what I would see on the other side of the mirror. Notice that it's the same distance away from the mirror, just on the other side of the mirror.
Here's our math picture from my life. This is gnocchi. We made Italian potato pasta using 1-inch cubes.